Okay. More and more people are joining remotely. You need to have, a reasonably valid reason for that. The expectation is that you are in class and that you participate there. But, I know people have things that come up, and that's why I make sure the recordings are available whenever possible, that type of thing. But please let me know in advance. Said this last week, and it's still happening. I had two people, notify me that they would be joining remotely, but right now I see like six of y'all. So just make sure you do that. Also, we're missing several assignments on the receiver equalization project. So make sure you're getting those in. And then I believe that the next one is due tomorrow, maybe something like that. So that should be assignment 7. Let's see, that's on error control coding. And then I am releasing another one. I just released it, and that one is on source coding, as I talked about last week. We're just going to focus on Huffman coding, and it's pretty straightforward if you look at the help files for the various functions that I'm calling out for you to use. Here's one where you actually create the Huffman encoder, and you look through this, you're going to use something similar to this. And if you look up the encoder, again, there's some example code in here that you can follow, and I think you should be able to kind of follow what I'm doing in the assignment. Here's a random source. We've used rand and randi and that type of thing in the past to create random bits, random integers, and also here you can use this to create a sequence that's m by n that's drawn from this alphabet with these probabilities, right? So that's exactly what we're dealing with. And when you look at their example, they actually call this. Okay, so my write-up, what I'm asking you to do is just a little bit different from that. We're going to first of all make sure, some of y'all in the beginning, I was just looking for source code. Now at this point, we've evolved and learned a lot of things, and now I'm asking you specific questions and that type of thing. So make sure you're addressing those in your report, and that at this point I'm expecting both a kind of a written report. These don't have to be long. They're not 10 pages. They're just, a few things here, and you don't have to do a super fancy job on it. I appreciate when you do, but it's not really necessary. But just make sure you have the information in there, right? So here what I want is a report that describes your process to follow all these steps. I think I have 11 steps here. Right, and actually some of these are repeated here in step 9. So you'll briefly describe your process. Now that should mostly be in your source code, but then explicitly answer the questions in boldface below. Right, so here we're going to use this Huffman dict, Huffman encode, and Huffman decode to encode and decode a source alphabet according to the following, right? So here I'm giving you a set of symbols 0 through 6, and then probabilities associated with each of those symbols. And then I'm going to ask you, what is the minimum number of bits to represent these symbols, right? In an uncoded fashion, right? So, and here I'm saying here, use this hint, right? So figure out what argument to put in there and how that's going to produce the output. But basically, you're going to look at that and it's like, okay, how many bits do I need to represent? And you can, recognize that these are integers, right? And you just need to represent these 1, 2, 3, 4, 5, 6, 7 different integers, right? So that's a hint. How many bits are you going to need to represent all those? Then you're going to create a source that emits the following symbols, right? So I'm giving you these symbols, and yes, they're all drawn from this alphabet, and they follow this probability. Actually, it follows it exactly, right? And it's not always going to be the case. These are estimates of the probabilities, but I generated these, so I believe that it follows these probabilities exactly. So then, how many bits does it take to transmit these symbols without source coding? Right. So you're going to look at these. All right. So use this information, right? And then, how many symbols are there, right? And that's the number of bits per symbol. That's not, you can do a length on this array, create an array with these symbols, and then just do a length, and that should give you the answer there, right? And then using the previously created encoder that is actually returned to you in the form of a dictionary, right? So when you do this Huffman dict, you're going to present it with these symbols and these probabilities, and it's going to return a dictionary. And then, so you're going to use Huffman Enco to encode the source symbols. Then answer this question: how many bits does it take to transmit the encoded symbols? Right. So this is going to return you back a code, right? That is specifically using the Huffman encoder to encode all these symbols. And so when this returns, it's going to be that whole code, right? So just count the number of bits in that. Then use Huffman decode or decode to decode the code, and then just make sure that they match, right? So the ultimate input, all these source symbols, you should get that exact array back after this. And then now there's just 20 of these, but let's do what did I say, 10,000. Okay, so I'll put a comment in there to make sure it's easy to see. So use this RAND source that we talked about, create a input signal that is 10,000 symbols long, right? So it's going to take this alphabet with these probabilities and generate a sequence of 10,000 of these symbols that follow these probabilities, right? And then go back and answer maybe as 4B and 6B, how many bits does it take to transmit all of those symbols, all those 10,000 symbols, right? And then how many bits does it take to transmit the encoded version, right? And then again, verify the results. And then calculate the entropy of the source. And I've given you a hint there. And then what is the average rate? Now here, you're going to examine the dictionary and look at the lengths of the different arrays. But when we average something that has non-equal probabilities, we need to weight by the probabilities. So take that into account. Let's see, let's reconnect here, see if it'll let me back in. Okay. Um, so if we look at my code here, then we've got, um, we start with a clean slate. I create symbols 0 to 6. Okay, so I gave them to you in the assignment in a nice numerical order. They're numerical symbols, they're in order. So we can use a shortcut here and just do 0:6. Symbols could be more abstract than that. They could be an A, comma B, comma C, but here we're going to call them integers from 0 to 6. And then I just format the probabilities in terms of this vector and call that P. Now I calculate the bits per symbol, and then we encode that as a dictionary, and then I'm going to produce the minimum number of bits. Then I'm going to create this input signal. And again, I just copy and paste that in there and format it, get rid of the commas, and put it into vector form, and then print out the number of bits then needed for that. And then I decode it, or I'm sorry, I code it. And then print out the total number of bits for the coded version, the compressed version, right? And that should be smaller, right? So let's see, what did I get, right? So 60 in the non-coding sense, and 50 in the coded compressed sense. So hopefully you get something that's substantially the same as that, right? And then I let's change that to 10,000. Then I also convert the input signal to bits, and I can calculate the length of that, and I can I actually back here, let's see, I decode it, and then I check to see if those arrays are equal. This will do a element by element comparison, and then I print out those results. And these are just calculating some lengths and that type of thing. So that's you'll see that in the example code in MATLAB description of these functions. And then we do a big array, and then I calculate the average entropy. And I haven't calculated the average rate yet, or the average length of the code, but you're basically going to look at the dictionary, right? So when we do this Huffman dict command, it's going to return back a dictionary, and it's going to have your symbols 0, 1, 2, 3, 4, 5, 6. And again, these are integers in our case, but it could be A, B, C, D, or it could be red, blue, green. It could be car, truck, motorcycle. All right. So this encoding is doing things in a very abstract manner, right? And then each of these is encoded, right? So now I didn't give you, I'm not giving you these symbols in order of, let's say, ascending or descending probabilities. I just kind of put numbers down and made sure they summed up to 1, right, as far as total probability. You should be able to verify, though, that this is a prefix code, right? So here's 3 shows up the most. I think it has a probability of 0.4, and so it's going to have the shortest code. And then 1 and has a probability of 0.2, and so it has the next shortest code. And then 0 and 2, both and 6, all have a probability of 0.1, I think, and then 4 and 5 have a probability of 0.05, right? So you can see that, yes, that kind of makes sense, that it's length weighted. So what you need to do is learn a little bit about the MATLAB cell array. It's a little bit abstract, and again, it's the cell array is useful when you don't have a rectangular array all of the same data type, right? So you can stuff in different data types, and it doesn't actually have to be rectangular. It can be what we call ragged, or maybe in some contexts that would be sparse. But so what you'll want to do is be able to kind of index into here, right, and get the uh, look at these different aspects of the array. And I didn't mean to do that. That's what I meant to do, right? So now this is, so you'll note that this whole thing is a cell array. So each of the elements are cells, right? So now we can use our array indexing and get each of these. So you might do a for I equals 1 to you know 7, I guess it would be, right? There's 7 elements there, right? 7 by 2, and then look at dict, and it would be I comma, and then we want to look at that column 2, right? And so sorry, mixing languages, that would be Python. And there, so now we're printing out each one, but now you need to index into there and either use length or number of elements, numl, to calculate that. But then make sure you're weighting it according to the probabilities of those values, right? Just it's similar to what's going on here, right? All right, so that's the assignment, and hopefully that goes pretty easy for you. I think maybe the tricky part will be to learn a little bit about that cell operation of the MATLAB cell arrays and being able to extract elements from there. But just read that a little bit, and if people are having problems, I'll talk about it on Tuesday. I'm making this one due next Tuesday at midnight. I think that's Tuesday, right? So is today the 9th? Yes. So yeah, a little bit quicker turn on these things, just so we can get caught up. All right, so if we're having problems, again, if you're having problems on your assignment, the expectation is that you make an appointment with me and we go through it, right? And if you turn something in that's incomplete, that's without have contacted me in office hours and made an appointment or sent me an email, asked for help, it's kind of indicating to me that you're not taking the assignment seriously, right? So I know you're busy. Second semester senior year is a super busy time, but I want to make sure you're taking my course seriously. Honestly, that's it. So as we talked about at the very end of lecture on Friday, we're going to look at spread spectrum today. So so the purpose, the concept behind spread spectrum is to use more bandwidth than we normally need to, right? So Claude Shannon came up with this capacity relationship that has bandwidth as a parameter in that equation. And the idea is that spectrum is a scarce resource, and so we want to use it considerately. And so we're going to normally use the minimum bandwidth it takes to transmit our data at the needed rate, right? If we need to send 1 megabits per second, of data to fulfill whatever mission purpose we have, and we have a certain amount of signal noise ratio budget to deal with, then that's going to determine the bandwidth we need to use, right? We might use some sophisticated error control coding. We might use some source coding to compress our data to begin with. We might use these bandwidth efficient modulation schemes. We're going to use all these tools that we have to normally send that data rate using the minimum bandwidth possible. Again, I'll toss out that like cell phone companies, when they buy spectrum at auction from the FCC, then they can spend billions of dollars to get like nationwide coverage to run a full-blown cell network, right? Cell system. So it's very expensive and becomes a non-trivial part of your cell phone bill as a consumer. So, so all that said, we're normally working to use the minimum bandwidth possible, but there are times when we purposely use a lot more bandwidth than that. And that sounds bad on the surface, and it would be wasteful if we just did it haphazardly, but there are ways to do it in that everyone kind of benefits from it. So first of all, why would we do that? Well, we can overcome narrowband jamming, and that might happen in an adversarial type of relationship, like you're in a conflict with another nation state. Let's call it a full-blown war, right? And communications is an essential part of trying to win a war against your adversary, and it goes way, way back, right? As far as long as we've been fighting wars as a species, we've won or lost those to a part based upon how effective we can communicate between our commanders, and all. So it's to the adversary's interest to try to jam your communications, right? Jamming is hard. And so we end up in kind of an arms race in terms of trying to figure out better ways of jamming, and then on the other side tries to figure out better ways of communicating in face of that jamming, and so on, right? So we want resilient communications in the face of adversarial jamming, but that's not always the reason. Even in a commercial or consumer type application, let's say just like Wi-Fi or Bluetooth, both of those can operate in around 2.5 gigahertz, 2.45 gigahertz. There's an unlicensed band, meaning that in order to transmit in that band, you don't need to go and get a license from the FCC. Normally you do. When you are operating your cell phone, the cell phone carriers have gone through and made sure that they have licenses to operate in that spectrum. A broadcast TV channel or FM or AM channel, they have a license to operate in their spectrum. And that license governs where their transmit antenna can be, how tall it can be, how much what we call its effective radiated power, which includes not only the power of its transmitter, but also the antenna gain and that type of thing. And then how much, what frequency channel they've been assigned. And normally the bandwidth is kind of standardized. For example, in FM channels, the channels are spaced at 200 kilohertz steps, if I remember correctly. Been a lot of years since I dealt with that. But in unlicensed spectrum, we just need to make sure that maybe the equipment has been certified to not cause a bunch of interference, and that it's emitting energy in the unlicensed band, but not emitting too much energy in other licensed bands and in other bands. But beyond that, anyone can pick up a Bluetooth, let's say a headset or a mouse or something like that, and use it, and it's transmitting, right? And so is your Wi-Fi access point and all. You might have a smart home and have a bunch of Zigbee radios around. These are all operating in that same frequency band, the 2.45 gigahertz. There's another one around 900 megahertz. There's another one around 5 gigahertz. And so I'm just using 2.45 as one of the more common ones, right? And so now uh, there's some structure to these unlicensed bands, but the idea is that you can operate there, but you have to accept interference from anyone else, right? And so we are working in a non-cooperative manner. I don't ask my neighbor what channel his Bluetooth is operating in. I don't ask him permission to use my Bluetooth mouse or pad or something like that. I just do it, right? And the systems automatically handle it. So it's non-cooperative, and it's operating in an unlicensed band. So they're potentially interfering with each other all the time, right? So we're using spread spectrum techniques to overcome those interferences. That's not always narrowband jamming. They can both be spread spectrum type signals. And in fact, that's common, almost necessary in some of these unlicensed bands to use spread spectrum. And then another use case for it is to overcome fading via frequency diversity. Right. So again, fading is when we might have a signal that comes from your antenna, but one bounces off of a wall, another bounces off the ceiling, another bounces off of a truck that's rolling by on a street outside your house or apartment or office or whatever, right? It can bounce off of buildings and mountains and whatnot, right? And so each of those rays, as that signal travels in a wave from the transmitter to the receiver, may take a different path, and each of those paths are different lengths. That means that the phase at which it arrives at the receiver antenna may be different, right? Is very likely to be different, right? And so sometimes they're going to add, but a lot of times they're going to subtract or cancel out each other. When it cancels out, there's a big loss that you're seeing. We call that fading, and but that tends to happen over a very narrow band because phase over a certain distance is related to the wavelength or the frequency. So as you change wavelength or frequency, right, there are reciprocal relationships with respect to each other, and so that phase will change, and so they signals might cancel at a very specific frequency, but if you tune that frequency away a little bit, then they won't cancel, right, as much. Their phases will add differently. So we'll see a picture of that in a second. So maybe one other use case, maybe there's more, but another common one is when you want to use maybe covert communications, and this is a little bit of a arms race type of thing. Also, you may not want your adversary to know that you're actually there and transmitting. As it turns out, we have missiles that have homing on them that will home on to, let's say, a radar installation. Radar and communications are related. Right? They're often both using electromagnetic waves. So there's a lot of concepts that are shared. And radars often use spread spectrum technology also. So an example there would be if you want to destroy an enemy's radar installation, you can put a homing receiver onto the nose cone of your missile, and loop that into your guidance system and just home in on that energy from the radar, right? And so that missile will target that radar, and you can just let it go. And the the way that the enemy will adversary will deal with that is they'll turn their radar off, right? But then there's nothing for the missile to home in on. But of course, now they don't have the radar to be able to track you, right? So there's we can use spread spectrum to try to make it harder for that missile or homing receiver to find us, right? So we're going to spread our energy out over more frequencies, and therefore it's just makes it harder for them. It's not impossible. That's why I say it's kind of an arms race type of thing. You may want to do this type of covert communications also, so that it makes it harder for anyone not just to jam you, but to even know that you're communicating, right? So, all right. This slide talks a little bit more about this fading due to this multipath interference, again, where we have multiple paths of different lengths from the transmitter to the receiver, right? And so propagation loss, this is a kind of spectrum analyzer display of frequency versus kind of amplitude or response here. And at a central frequency, maybe we've got a nominal type of thing, but and this signal here measured somewhere after the receive antenna, but is going to be the superposition of the amplitudes are combining in a vectorial way, amplitude and phase, from all the different paths that are possible, right? And some of those paths will have lower amplitudes because maybe what they reflected on was absorptive of that energy, or maybe it just took longer and spread out more, right? But they're combining in a nominal way. But you see that at certain frequencies, boy, we just had bad luck, and the signals just cancel completely. But fortunately, that happens over a very narrow bandwidth, right? Again, this is because phase with respect to path length is frequency dependent, and the dropouts are very narrow band. So if we're trying to communicate right here, oh my gosh, right? So that's down 32 dB from a nominal 0 dB line up here, right? That's terrible. Well, maybe it's 31 dB, right? But that's a lot. That's 1/1000th of the power that we're seeing. 30 dB down would be a 10 to the -3, right? So 1/1000th of the power energy that we're receiving there. That's terrible, right? So how can we operate in this kind of environment where we just might get very unlucky, and we don't want to rely on luck, right? So we're going to spread our signal out over here, and if we have some kind of notches in our signal, but that energy is spread out over a broad bandwidth, then maybe we can still communicate effectively, right? So, all right, I mentioned covert communications already. Here we maybe define some terms you might see here. So low probability intercept, LPI, this is originally applied to determining if a radar is pointing at you, right? So that might be a radar warning receiver. Can be also used in communications, but we're really trying to say, hey, is someone illuminating us with a radar? So, and I should note that some of these terms have multiple meanings. Sometimes low probability intercept in the comms area is really more meant to talk about more of an anti-jam type of thing, where your intercept would be someone jamming you and stuff. So there's a little bit of sloppy usage of some of these terms sometimes, but another term that you'll run across is LPD. So you might see something specifies LPD, LPI type of thing, but it's often used interchangeably with LPI, but can additionally mean that the signal is not only perceived, but also characterized, right? So in a radar situation, we might want to know what its pulse width is, what its pulse repetition rate is, what its frequency, what its power, what its maybe antenna rotation rate is. In a communication system, we might want to know what kind of modulation it's using. Is it using quadrature AM modulation? Is it using FSK? Is it using more of a phase modulation? And we might want to know that information so that we can maybe effectively jam it or learn something about it, whatever. So, and then, anti-jam is the idea that you're making your communications hard to be able to defeat or to jam, right? Making it harder on the adversary. All right. So there's three main types is the way I break it up for spread spectrum types. We can spread in terms of frequency hopping or a direct sequence, or we can chirp our signal, right? And then we have kind of some related concepts that build upon that. But let's go through these real briefly, and then we'll dive into them more in depth, right? So frequency hopping. We can have fast or slow, and basically we're taking that signal, and instead of operating only on one center frequency all the time, we're going to change what frequency we're transmitting on and hop around within still kind of a finite band, but maybe that band is 200 megahertz wide, but our signal is only maybe 10 megahertz. And so we can hop to one of those, if we break that 200 megahertz up into 10 megahertz chunks, now we've got 20 different channels that we can operate over. And so we hop to a different channel at a different time. And we might, send in terms of fast hopping, we might send a fraction of a symbol over that at that particular channel, and then move to another channel and send more of that symbol, and then hop to another channel and send maybe the remaining part of that symbol, right? Versus slow hopping, where we would be able to send multiple symbols per hop, right? So we look at our transmitter, we're going to take our data and maybe we source encode that using Huffman encoding, whatever, and then we now we have bits. We might do some error control coding, but then we're going to modulate it, right? And now we have modulated symbols. Instead of just transmitting those symbols at a single frequency, we're going to take those symbols and send them over multiple frequencies. Now the question is, on slow frequency hopping, we're going to send a bunch of symbols per hop, and then we're going to hop to another channel and send a bunch more symbols, and then hop to another channel and send a bunch more channels. Versus fast hopping, we're going to break that symbol up, each symbol up, and send portions of that symbol at different frequencies, right? A direct sequence is when we're going to multiply, or let's talk heuristically first, right? We're going to take our modulated symbols and we're going to chop them up. with a sequence that's much faster than the symbol rate is, right? So if we got a symbol rate of 1 megahertz, maybe we chop it at a 10, we'll call it chips per second, or 10 times that. I'm sorry, 10 mega chips per second. And when we do that chopping, we might like in one instant multiply it by a +1, and then in the next chip we might multiply it by a -1, right? So that's flipping the phase by 180 degrees or pi radians. And so we might do that, and we might, kind of naively, we might just alternate plus minus plus minus plus minus, or we might use a more sophisticated code. Maybe it's plus plus minus 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 plus minus minus or something, right? So, and then the third type is a chirp, where we can take a symbol and we will, let's say, do a linear FM or frequency modulated chirp while we're transmitting that symbol. And so instead of maybe hopping to discrete channels, we're ramping the frequency while we're transmitting that symbol, right? So that would be more of a chirp type of thing. Now, building upon these, we can have related concepts, including CDMA, or code division multiple access, and that's building upon a direct sequence, but we're using unique orthogonal codes. So one user might have a particular spreading code, the sequence of pluses and minuses, right? And that's a little bit more sophisticated than just plus minus plus minus plus minus, right? And so I give you one code, and I give myself a different code, and it turns out that our codes are somewhat orthogonal to each other, so we can both communicate in that same band at the same time. But we won't interfere with each other because I've got my code and you've got your code. We'll dive into this in more detail later. But now we're kind of going back to this idea that, oh my gosh, we're using more bandwidth than Shannon says we need to. Isn't that bad? Well, it is, until we develop techniques so that multiple people can operate over this broader bandwidth at the same time without interfering, right? So now it's okay that we're using broader bandwidth, and ultimately we're still kind of constrained by the Shannon's capacity theorem, but more like spread out over different users, right? So we're just kind of divvying up the spectrum in a little bit different way, and being able to do this in a coded way, right? With this code division multiple access. Then we also and that was super popular in 3G and some 2G type systems, right? And still used a lot today also. Our 4G and 5G and soon to be 6G cell systems, and most of our more modern Wi-Fi variants, and HGTV broadcast, and blah blah blah, lots of things are using orthogonal frequency division multiple access, and we'll look at this in one of our later lectures. It's coming up. So it's another way of kind of spreading our information over broader ranges of frequency, so we can deal with jamming or fading or these type of things, but also at the same time allowing multiple people to communicate at the same time. All right, so I've used this term here, this chip concept, a couple of times. So let's briefly try to define this. A chip is a concept, particularly in frequency hopping spread spectrum and direct sequence spread spectrum, where the pseudo-random sequences involved in spreading the spectrum are composed of pulses called chips of a fixed period that govern the evolution of the sequence. Right. So in frequency hopping spread spectrum, I'm talking about how we're hopping from one channel to another. Right. So that hopping sequence, or the sequence that governs what channel am I going to hop to next, and how long am I going to stay on it, right? So that how long is this fixed period, and what channel I'm going to is part of this pseudo random sequence. And it might be, we might number our channels, 1 to 20, or 0 to 19 or something. And I might hop from 2 to 17 to 12 to 13 to 4 to 18, so on, right? And then we would want that to kind of look random but be deterministic, right? That's why we're calling it pseudo random, right? Because we're going to see that we need to replicate that same sequence at the receiver to kind of despread things, right? So in the case of this direct sequence, again, in simplistic terms, we might just multiply by a plus or minus, or a 0 degree phase or a 180-degree phase. But we don't just simply alternate. We might use some specific sequence, pseudo-random sequence of those, right? All right, so let's dive into frequency hopping a little bit more. So we sequentially hop to a different discrete frequency within a large band using a sequence known to both transmitter and the receiver, right? So this is a pseudo-random sequence that's specifying which of these discrete frequencies to hop to, right? Sequentially. And both the transmitter and receiver need to know that sequence, and they actually have to synchronize to that sequence so that the receiver knows where the transmitter is going to be in frequency to be able to switch to that channel and measure the information, the energy there, and do the whole demodulating process, right? So since we're already kind of switching frequencies, we often use frequency shift keying to modulate the symbols, right? So we can do FSK within frequency hopping. Doesn't have to be FSK, but that's often the solution, easiest to kind of wrap our heads around. We can achieve multi-user communications via at least semi-orthogonal. I mean, ideally orthogonal, but we might relax the terms on that a little bit. And these hopping sequences, and what we mean by that is that if we have 10 users hopping within a particular band, if it's purely orthogonal, we will know that at no instance of time will any of those users be operating or transmitting or receiving on the same channel. They're always on a different channel. And so we're all hopping together, but to different channels, and we're never hopping on the same channel at the same time. If we did, we'll have a little bit of interference, right? So that's hard to synchronize to and accomplish, and that's why a lot of times on these systems, whether it's frequency hopping or CDMA or whatever, we should really qualify with semi-orthogonal. But some examples. I mentioned Bluetooth. That's a frequency hopping system. In the military world, we've got Link 16, an older system called SINGARS, and JTRS. JTRS. JTRS is how it's pronounced, jitters. And that's the Joint Tactical Radio System. So Link 16 is used like to communicate between aircraft and satellites and maybe Navy ships and that type of thing. And like I say, SINGARS is similar It's supposed to be a joint across different services, but the Army uses that a lot, and it's a little bit older system. All right, so let's look at a FSK frequency hopping system and how we might build this up, right? So we've got this frequency modulator, right? So all of our other receiver function or transmitter functions are to the left here, right? The source encoding, the error control coding, that type of thing is all to the left here. But we go through a frequency shift keying modulator. So right out here, we've got symbols. And that might be an M-ARRY type of system, right? We might be using mapping multiple bits to multiple one of many different frequencies, right? And then typically this might be done at more of a baseband or lower frequency, but maybe we need to transmit at 5 gigahertz or 6 gigahertz, something like that, right? So we're going to use a frequency up converter. We're going to use some electronics and some mixers and some local oscillators or whatever to up convert that, right? So we show that coming in here is just like we talked about last Friday about when we talked about intermodulation distortion. We reviewed how our mixers work with that nonlinearity in it, and the output of this can be a sum or difference or multiple of the frequencies coming in, right? So same concept there. But now instead of just sending in a single frequency to uplink or up convert this information signal to, then will allow us to be able to change the frequency. And we start to call this synthesizer when we want to be able to change it quite rapidly, right? In the old school days, we might have a knob or some push buttons that we change the frequency on, or turn a knob and we switch from one frequency to another. But now we can synthesize any frequency very rapidly, and we can jump to these different ones, right? So this might be a fairly sophisticated system right here. You might spend your career developing just this block right there. But we then run into this synthesizer a sequence that's generated by this pseudo noise generator or pseudo random generator. And again, that's going to operate at on a particular period, that chip period, but emit a value that is pseudo-random, but is deterministic still, right? So it's not random; it just has kind of random properties when we look at it, right? And then we transmit it over the RF channel, so there's going to be some power amplifiers here and antennas and more antennas, receive antennas, and maybe some LNAs, and then we're going to down convert it, right? Same deal. We've got a frequency synthesizer here and a pseudo noise or pseudo random generator. And then ultimately, once it's down converted, we can run through our demodulator or detector, and then the whole rest of the receiver all to the right of this. Now, just note that these things must be identical and synchronized to the transmit pseudo number generator. And so also, if there's significant propagation delay in this RF channel, then we need to adjust for that so that as this frequency is changing, we can exactly match that timing and down convert the signals, right? So there's a little synchronization that's going on here. So here's maybe an example. We can create a grid now, and we might call any of these grid locations a slot that we're communicating in, and that's going to be a function of both time and frequency now, right? So I've drawn in green here the maybe a sample hopping sequence of a particular user, right? And this evolves in these discrete time steps or chips. And so we might operate at this frequency channel during this chip, and then switch to this frequency and then this frequency. And again, if it's fast hopping, we might take uh, 5 symbols, 5 chips to transmit one symbol, right? And then we need to do another 5 to get the next symbol. If it's slow hopping, we might send maybe 5 symbols during this chip and then switch to another channel and send 5 symbols and then switch to another one and send another 5 symbols, right? And so on. Now, if we want to have another user operating in here, then we would develop a sequence generator that's hopefully orthogonal to this particular sequence, right? So we might hop from here to here to there, as long as we're stepping into a unoccupied slot each time, we're good, right? And then how many of these can we do? Support? How many users can we support in here? Well, it depends on how many channels we have and how good of orthogonality we can have with all these different chips, right? And what we want is really long sequences, right? So all right, let me get into some math here. So for a symbol period, let's call that T sub s, frequency shift keying symbol, right? So we're modulating this using FSK. Then let's look at the time domain representation of that. So we'll have a cosine carrier, and it's got a certain amplitude to it. And now we can either modulate the frequency or the phase. And let's say we modulate the frequency, and so we'll keep that constant. Uh, Remember, we looked at those, and we even looked at maybe a constant phase frequency shift keying technique and that type of thing, right? So this whole idea can get pretty sophisticated, but let's just assume that we're using different frequencies here, right? And so this M will, T is going to be in these MTS sampling symbol period chunks, right? So M is an integer here, right? So now we can choose a particular frequency. So we've got our carrier frequency, and then we can have a either plus or minus, let's say 1/2 delta omega. So we're switching on either side of this carrier, or we can have 3/2, and up to m minus 1 divided by 2, right? So we'll have capital M, and so our omega sub m could take on any of these values here, right? So there's commas here, so this is showing the different values it can take on, right? So that's just generic FSK modulation. Right? Now, during each chip period, we'll call T sub C, the synthesizer output. Now, this synthesizer frequency hopping is going to follow some hopping sequence, right? So it's got a nominal or this WM and this hopping sequence. So we'll shift this according to this hopping sequence, right? So in fast hopping, we'll have this chip period is much smaller than the symbol period, much smaller, so that we'll have many of these chips during a single symbol period. And slow hopping, the relationship is reversed, and maybe it's equal, or you might send 1 symbol per chip time, that would still be considered slow hopping, or you might send a few symbols per chip time. All right, so now let's start to look again. Let's get back to our motivation, why we're doing this. Right, so let's say our bandwidth to achieve a particular FSK is this BFSK, and let's define a L spreading factor, and that's going to then create a bandwidth for our frequency hopping spread spectrum system. Right, so then we're going to assume that we have a jammer J producing interference I. And so this is kind of like energy to noise, EBNO, or signal to noise ratio. But now we're really talking about interference. And the interference is no longer this AWGN, additive white Gaussian noise, but it's maybe, specific energy in a narrow band type of thing, right? So, or a broadband. So here, if we just look, we want to know what our energy per bit to ratio to the interference energy, and let's just look at it in a narrow band situation right now. So we'd have that energy per bit, and that'd be divided by the power in the jammer divided by the bandwidth of the symbol, right? And so again, we're converting to power spectral density type of thing, right? So here we'd have the EB divided by this PJ, and then this guy, since he's in the denominator of a denominator, he goes up into the numerator, right? So so we've got this, and but now with the jammer's broadband, we now are looking over this chipped bandwidth, right? And so our EB is this L times the energy per bit divided by the this interference. Okay, and actually, maybe this is not the best way of saying it. So if we're forcing that jammer to operate over a broadband area, right? So if we're now spreading this signal and we're saying, okay, now I want to jam this, and I've got to jam it over that broad bandwidth, then now I've got this relationship here where this energy per bit relative to the interference, normally we want this to be a large value, right? It makes it easier to demodulate. Then this is multiplied by the bandwidth of the chip versus the bandwidth of the symbol, right? And we're going to spread it, right? So that is now L, right? So by spreading our signal, it forces that jammer to operate over a broader bandwidth, and that means that our energy per bit for a fixed amount of power here is going to be improved. The signal to interference ratio is improved by a factor of L. Okay, so let's look at partial band jamming, because that's maybe the more typical case. It's harder to build a jammer that operates over wide bandwidth, so let's just transmit a cosine tone, right? So it's ideally a delta function, right, mathematically, but let's just emit a lot of power at a particular frequency, right? So we'll call that jammer narrow band, but it's powerful enough to force the bit error rate to be equivalent to a coin toss, right? 0.5. And so now you're guessing, right? So and that's normally about as bad as you'll ever see, right? So it kind of goes back to your assignment. A lot of y'all ended up on this. I guess it was assignment 6. You would calculate bit error rates of maybe 1 or 2 or something like that. It was just a misunderstanding of how the bit error function worked, and you were scaling it by the length of the symbols instead of the length of the bits. But if you end up with a bit error rate of greater than 0.5, well, you're doing worse than guessing at that point. So you probably have something wrong in your simulation. That's kind of an aside, right? But at 0.5, you're essentially just flipping a coin, right? So, but so that jammer would then therefore be effective, right? If we've done that, and let's do slow hopping. So we're going to set our chip period to be the same as our symbol period. So now we're running out of time here. I really went long here. Sorry, so I'm going to hand wave my way through this, but we're basically won't derive this, but look at this. You're saying that if your jammer doesn't know what frequency you're hopping to, right? You've kept your sequence secret, and so it's just going to jam at a particular frequency. So it's going to wipe you out once every L hops, basically, right? So if you're hopping around and your spreading sequence is L, so you're hopping around there, so you can maybe come up with this type of relationship here. And again, not gonna. I'm just going to skip over this here a little bit, but your probability of an error now due to this very effective jammer is scaled down to 1 over 2L. Instead of being 1/2, right? The probability of an error being 1/2, it's 1/2 divided by L. So we're driving that probability of error down. That's assuming that this jammer stays at a constant frequency while you hop around. So now consider a fast hopping system where our chip period is much smaller than our symbol period or rate. The chip rate is much faster than that, where each symbol is sent over a subset of L bands. Now, let's just kind of get to the point. We'll kind of define this L hopping sequence as a ratio of those periods. And so a symbol will encounter partial jamming with probability of this LH over L. What do we mean here is that if that symbol's energy is spread over L different channels, that jammer is going to wipe out 1/11 of the symbol, right? Okay, well we're scaling it here with this LH and L here, but if there's L different channels and we've stepped to L over L sub H channels within this period, then we're scaling that down, right? So we're only encountering this jamming with a probability of this, right? So we can approximate a binary frequency shift keying signal's performance by assuming its energy is wasted or discarded when jammed. But during the other times, it's not wasted, right? So we're just losing a fraction of its energy. And so when we integrate things and stuff, we're really like scaling its energy per bit by this L sub H minus 1 over L sub H, right? So it's a little bit of a fraction there that's scaling its energy. So we lose a little bit of energy, but we still get a lot of that symbol's energy because we're stepping away from the jammer, right? So, and we might not step on a jammer at all. That's kind of what all this math is doing. But if we do, then we're only going to lose a fraction of it, right? And so then we'll go through again. If L is much larger than 1, some of this math simplifies. And let's cut to the chase here. So here our probability bit error is equal to this. If you go back and look at your FSK stuff, it's essentially immune to narrowband jamming, right? If L is large enough, if we're stepping over enough bandwidth, enough different channels, then we'll have essentially an immune to this, right? So the fast hopping is better than the slower hopping, right? And all right, then let me try to at least present this direct sequence subsystem. Here we're going to have a pseudo noise code generator, pseudo random, pseudo noise, and it's going to generate this C of as a function of T, this chip pulse generator. We're going to take maybe a Comm type thing here, right? So this might be a 4 Comm or a 16 Comm, whatever, right? So some level of Comm modulation, and we're going to multiply it by the CT, where it's evolving chips much faster than the symbol rate is. And so this rate of this, right? So we take the reciprocal of its chip period, that's its rate, and that is going to dominate how fast this symbol is changing, and therefore how wide a bandwidth it is, right? So we're spreading this by essentially chopping it with this chip sequence. We're chopping it up, and therefore we're have things changing here at much faster rate, and we're spreading that bandwidth out, right? And then we chop it again with this same sequence, and we recover it, right? So if we've got this system of pluses and minuses, we can kind of recover it here to stitch it back together and simply have that sequence of Comm signals coming out there. So we can generate this with some long linear feedback shift registers. So these are some memory locations, and our value here is stepping across, but maybe we sample the output and then sample some memory location, and we sum those together again in a modulo 2 type of situation. So we might have a plus or a -1 here coming in, or maybe it's zeros and ones that we map to plus and minus things. And we want long periodicity here, right? So we want the shift range to be, long noise-like autocorrelation, right? So when we correlate things, then if we autocorrelate it, it has a peak at the no shift version, and then very low energy everywhere else when we slide things across in this autocorrelation approach. And then we want a set of orthogonal sequences with very low cross correlation, right? So similar to in the frequency hopping thing, we don't want to step on the same frequency at the same time. We want these guys to have very low cross correlation. So that's just where they're used. And then finally, we can have a chirp system, and we can multiply are transmitted with this chirp, and then we can transmit it, and that's going to spread that energy out over this range of frequencies here. And then when we receive it, we kind of multiply by the inverse of this chip. We just flip it around. And in comms, it's more rare, but this LoRa, which is kind of a metropolitan area Internet of Things type of transmission system, it uses part of a more complex modulation scheme, some chirp spread spectrum there also. So, all right. So I know I really screamed past those last few slides. We'll try to touch base on those on Friday just to reinforce, and then we'll move on to fading channels and MIMO type communications. All right. We will see you on Friday.